This is a short tutorial on solubility as it is taught in the Level 2 NCEA curriculum. Ionic substances dissolve to some extent in polar solvents like water. And in order to explain this, we have to consider the existing forces both in the ionic lattice and between water molecules. Now, water molecules are polar, so they have a partial negative end at the oxygen end of the bonds and a partial positive end at the hydrogen end, called an overall dipole. What we need to be explaining is how that overall dipole causes attractions to the ions within the ionic lattice and thus disrupts the lattice as new forces form. The easiest way to look at this is to imagine in our brains what is on this simulation and explain it. So as you can see, the polar water molecules look like they're attacking the ionic lattice. The oxygen end, represented by the red atoms for the water, is the partial negative end, the most electronegative element being the oxygen, and it is attracting to the positive ions and pulling them out of that lattice. So it is breaking the ionic bonds and forming new attractions between the ions and the water called ion-dipole forces. The opposite is true for the hydrogen end of the molecule, which is the partial positive of the water molecules. Hydrogen being less electronegative. They are attracting to the negative ions and pulling those out of the lattice and carrying them away as hydrated ions, thus breaking the ionic bonds and disrupting the lattice. Now, for this to be the situation, what we have to understand is that the original ionic bonds and the original intermolecular forces between the solvent or water molecules must be weaker or at least only as strong as the new forces that are forming between the ions and the water molecules. The strength of those new forces relative to the existing ones in the beginning is what is allowing dissolving to happen. That is physically favorable. Now, it is not only ionic substances that we get asked to describe why they dissolve. We can sometimes be working with the molecular world or chemicals that we've drawn Lewis structures of and decided whether they are polar or non-polar. It is very important that you understand from previous parts of the standard that ionic chemicals are made of metal and non-metal atoms. The chemicals you've been working with in previous years of science when you've been using an ion table to construct formulas for compounds. Sodium chloride, metal, non-metal. Potassium hydroxide. Lithium nitrate. Magnesium oxide, those kind of chemicals. Now, when we move into the molecular world, we are talking about chemicals that are only made of non-metal atoms, discrete packages of covalently bonded non-metal atoms that are holding to one another, forces between particles being intermolecular bonds, the weakest type of bonding. Molecules like ammonia, a trigonal pyramid where there is no dipole cancellation, a polar molecule. CHCl3, a tetrahedral, where despite molecule symmetry, there is different strength dipoles within that molecule and therefore no dipole cancellation. Our acids like HF, HBr, HCl, our linear structures where one atom is very much more electronegative than the other. When we think about these polar molecules and the rule like dissolves like, so chemicals with the same polarity being able to dissolve in one another, we need to think about dipoles interacting with dipoles, not ions like in the ionic example. On the screen here we have a simple polar molecule where atom B is more electronegative than atom A, and that is set up a bond dipole where there is an unequal sharing of electrons. B has the bonded electrons more of the time. This causes those partial charges that we're familiar with, the symbol partial minus at the end where the electrons are most of the time, and the symbol partial positive at the end where they are not. Now, that is referred to as an overall dipole, and if we were to apply an electric field, we would notice that B, with its slight negative end, would orient towards the positive, and A, with its slight positive, would orient towards the negative. Now, this is exactly what happens when molecules interact with one another, except it's dipole to dipole interaction as opposed to the electromagnetic field or the electrostatic field. What we want to do at that point is to think about molecules and how we could draw those for examiners to make those new forces clear. If the new forces, the new intermolecular forces, because we're working in the molecular world now, are at least as strong or stronger than the original intermolecular forces between the solute and solute, the solvent and solvent, then the new attractions will form and the two molecular substances will dissolve in one another. This is ammonia down here with its slight negative and slight positive end, polar molecule. And if we were to draw water with its oxygen end facing away, slight negative, and its hydrogen ends facing toward, what we could then show is there is a attraction that forms between the two oppositely charged dipole ends. That is a new intermolecular force, and if it is stronger than those existing forces were, remember these are forming millions of times over because there's not just two molecules within a sample of these things. There's moles of molecules, large numbers of molecules. Those existing forces, if they're stronger than the original ones, then dissolving will happen and the molecular substances will form a miscible solution with one another.